title Newton da Namaskar. A very basic sheet though. So the first problem of the sheet is about two situations. There is a pulley here. There is a fixed horizontal ground, and this is a free end, and it's being pulled by a man here, and the mass of this block is given to be, okay, it does not matter, downwards. In the second situation, we have a fixed pulley, free end, there is a mass m here. All right. Now, what is being attempted? So there are these two pulley situations. In this situation, in each of these situations, we want to be able to raise the mass m by a height h in time t, right? Which means in both these situations I want to create the same acceleration on the two masses, right? Starting from rest, h is half at squared, h and t are the same. That means the acceleration produced is the same in both cases, right? In this case as well as this case, the same acceleration. Now, if this man pulls this down with a force F, right? Then the tension produced at all points in this string is going to be F. Now, given this, if I look at the free body diagram of mg, then mg like this, the tension in this string is going to be F, producing an acceleration A upwards, right? So this gives me F minus mg is ma in the first situation. The force required to produce an acceleration A in this mass, F plus A in the first situation, yes or no? Right? Look at this second situation. Suppose he pulls it down with a force F1. Then the tension produced at all points in this string is going to be F1. F1, right? This string is going to be F1. Now, if you look at the free body diagram of this movable pulley, right? Then there is going to be F1 and F1 like this. There is going to be F1 like this. Looking at the free body diagram of this, F1 like this and F1 like this, right? And what I do is, in my free body diagram, I include this string also, so that forces in this string would turn out to be internal forces. And there is mg like this. Looking at the free body diagram of this movable pulley, this string and this mass m, right? And what this should do is, this should give this mass, this entire unit should have an acceleration A upwards, yes or no? So very clearly, for the free body diagram comprising of the movable pulley, this string and this mass, the equation of motion is going to be 2F1 minus mg is ma, or F1 then turns out to be m by 2 into g plus a, which is half of F. That means the effort required here is half of the effort required there. Therefore, this is a better machine than this. Got me? That's the whole idea. That's the whole idea of using multiple pulleys. We don't use multiple pulleys for the heck of it. We want what they call a mechanical advantage. Right? Got me? Okay, let's look at the next problem. Clear? Problem 2. Fixed ceiling. There is a platform of mass 25 kgs and there is a man of mass 50 kgs here. There are two fixed pulleys. All right. And he wants to pull this string down. So this 50 kg person standing on a 25 kg platform, he pulls on the rope which is attached to the platform via these pulleys as shown, frictionless ideal pulleys. The platform moves up at a steady rate. Now what is it that I mean by a steady rate? Means constant velocity. Constant velocity. V equal to constant, or acceleration is 0. Acceleration is 0. Right? I want to be able to find the force with which the person pulls the rope. Force with which the person pulls the rope. What you need to do here is, okay, suppose the person pulls the rope with a force T. Then T turns out to be the tension at all points of this. T turns out to be the tension at all points of this. Yes or no? Now, think of the free body diagram that comprises the man. So if the man pulls the string down with a force T, the string will pull the man up with a force T? Yes or no? I also include in my free body diagram this second pulley, this third pulley I include in my free body diagram, right? Then I would have to take care of, well, there is going to be T like this and there is going to be T like this. So I have T like this and I have T like this. Yes or no? Right? And then there is Mother Earth 50 plus 75, 25, 75. So 750 newtons downwards, taking G equal to 10. 75 kgs into 10, 750 newtons downwards. Yes or no? And the net of all these forces must be 0 because 0 acceleration of this, and therefore 3T is 750. T therefore turns out to be 250 newtons. Got me? Reason I didn't want to draw the free body diagram of man alone or platform alone, because then the forces that they exert on each other would have to be highlighted. Those would have been brought into the picture, and I don't want to deal with them because I don't need them. Right? So might as well, if there is a force which I don't need, might as well have a choice of my system in a manner that that force turns out to be an internal force. Its representation will not be required. Right, so did you get me right on this? Why this choice of free body diagram is best for this situation? Got it? Sorry? Oh, you mean like this? It won't matter. It won't matter. All right. So option B, 250 newtons. All's good on this? So here we have another arrangement. This pulley, this end of the rope being pulled down with a force of 100 newtons. There is this movable pulley with a 5 kg mass attached here. Right, this is the arrangement that we have here. Now if the string is pulled down with a force of 100 newtons as shown, then the acceleration of the 5 kg block is going to be what? Very simple. If this is 100 newtons, that means tension at every point of the string is going to be 100 newtons. Right? It's going to be 100 newtons, yes or no? Isn't it? Now let me look at the free body diagram comprising this pulley, this short segment and this mass m, right? So very clearly, you know, there is going to be 100 here, 100 newtons. There is going to be 100 newtons here. Hundred newtons here. Mother Earth, 50 newtons on this 5 kg block, G equal to 10, right? So the net forces 200 minus 50, 150 divided by 5. That's the acceleration, which is 30 meter per second squared is the acceleration, right? 200 minus 50, 150 divided by 5. That makes it 30 meter per second squared would be the acceleration of this unit, right? Let me look at 4. So far so good, right? Not a problem? So problem number 4. There is this block of mass 5 kgs, right? And a force F of 50 newtons is applied on it. What's that squeaking noise all about? 50 newtons. Then there is another block of mass 10 kgs. And there is a pulley here, there is another pulley here, comes like this, there's a pulley here, goes like this, and like this, and this is fixed. This is fixed, right? This end is fixed. And then this string goes here. And then again, you know, it's fixed to some point here. This is the arrangement. And then this is the pulley attached here, right? Now I want to be able to find, this is one single string. I want to be able to find the tension in the string. I want to be able to find the tension in the string. Now, first things first. Say the acceleration of this mass is a1 meters per second squared and the acceleration of this mass is a2 meters per second squared. Right? Yeah, let's figure that out using string constraint. Otherwise, how would you know? Right? Now, if I look at this free body diagram of this mass, 5 kg mass, along with the two pulleys, then you know there is going to be T like this, T like this, T like this, and T like this. Yes or no? T, 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 T. Hey, one rule of the game, you know, it's not necessary that you need to follow this, but if there is a pulley attached to an inclined plane, or there is a pulley attached to a wedge, fixed to a wedge, then don't try and isolate these two. In the sense, don't try to draw the free body diagram of the inclined plane without the pulley or the wedge without the pulley. You can do that. But then in the process of isolating the pulley with the plane or with the block, you would have to then take care of the forces that they exert on each other. However, if I look at this pulley attached to this mass, then the forces that they exert, the pulley exerts on the mass or the mass exerts on the pulley would be an internal story, and we will not have to break our heads over it. Right? We will then need to break our heads over what the string is doing to this pulley, what the string is doing to this pulley, what the pulley is doing to the mass is inconsequential. That's an internal force will not participate in my equation, right? And there is a force F like this, which is 50 newtons. We need to first of all also understand, why there is need to connect A1 and A2. So I'm not right away, jumping into that. So what's the equation of motion? Of course there is, weight downwards and normal react. I don't need that, right? What would be the equation of motion for this? 50 minus 40 equals 5A1, right? That's the equation of this mass, right? Now, if I look at this mass, along with these two pulleys, these pulleys are integral with this mass, might as well have those pulleys stay connected to the mass, right? In which case, the 10 kg block this pulley, T like this, T like this, T like this, T like this, and causing it to have an acceleration A2 to the right. What would be the equation of motion for this? 40 equals 10A2. 40 equals 10A2. Yes or no? 40 equals mass into acceleration, equation of motion for this too. Now, T, A1 and A2, 3 unknowns, but how many equations? 2 equations. That means there is, and we have exhausted Newton's laws. Where Newton's laws will end, constraints will begin. So which means, I need to connect A1 and A2, which is a kinematic requirement for this, right? I need to then figure out the kinematic requirement, which is connecting A1 and A2. Yes or no, right? All right. Now let me forget all about these just to remove the clutter from here. All that I need to do is, I need to take this string and I need to apply the string constraint to the string starting from the point P all the way to Q. Yes or no? Let me assign to the nodes the respective accelerations associated with those nodes. With P, what would it be? 0. With this point, A2 to the right. With this point, A2 to the right. With this point, A1 leftwards. With this point, A1 leftwards. Sorry? House? Huh? Oh, sorry. I'm so sorry. This is moving to the right. This is A1 to the right. A1 to the right. Apologize. A1 to the right. Yeah. Then, what about this point? A2 to the right. This point, A2 to the right. This point, A1 to the right. This point, 0. Let me then customarily go through this entire string with the string constraint that I mentioned. I go from here to here, minus A2, minus 0. In the direction of traversal, minus A2, minus 0. Then I go from here. A1 minus A2. Right? Going from here to here. Then I go from here to here. That is minus A2, minus A1, minus A1. Yes or no? In this direction, minus A2, minus of minus A1 for this. And then this one then I go from here to here. A1 minus A2. Right? Here to here, A1 minus A2. And then I go from here to here, 0 minus minus A1. What does this give me? In terms of A1 and A2? Is 0. That means A1 equal to A2. That means it gives me A1 equal to A2. A1 equal to A2. Now that I have A1 equal to A2, I can solve for, put A1 equal to A2 equal to A, say. Then this A1 can be replaced by A, this A2 can be replaced by A, and I can solve for T. How much does T turn out to be? Huh? How much is T? 25 by 3? Okay, so A turns out to be 25 by 3. T is 25 by 3. Okay. T is 25 by 3. you can solve for A. Right? So how much is it? Oh, we had to find T only. Okay. So T is 25 by 3 newtons. Right? Solving these two equations. 8.33. Simple, right? Number 5. A situation like this, there is a wedge and there is this unit. This is referred to as B, and this has an acceleration given as 5 meters per second squared downwards. This angle is given to be 37 degrees, right? I want to be able to find the acceleration of A. I want to be able to find the acceleration of A. Suppose the acceleration of A is, obviously the constraint is A will move only horizontally, and you can see that when this falls down, this has to move rightwards, right? Now, look at this surface, PQ, where the contact is, right? This block B has a downward acceleration of 5 meter per second squared. This block B, right, represent this. This is moving down with 5 meter per second squared. Whereas this inclined plane is moving to the right with an acceleration of A meters per second squared. Yes or no? This is the common normal of the two surfaces, isn't it? This common normal of the two surfaces. Now for them to maintain contact, the acceleration of this B in this direction must be the same as acceleration of A, which is this inclined plane rightward along the common normal direction to maintain contact, isn't it? I'll repeat. See, that's wedge constraint. This is this surface, right? This has an acceleration A downwards, 5 meters per second squared downwards, all right? Whereas this inclined plane with which it's attached, this has an acceleration A rightwards, right? This is their common normal direction. This is their common normal direction. In order that this could maintain contact with this, in this direction they must have a common acceleration. That's the wedge constraint, isn't it? To maintain contact along the common normal, you must have the same acceleration and the same velocity. Have I taught that? Okay. So now all that you need to do is this is 37 degrees, as you can see, right? Right? So acceleration of this block B along this direction is 5 cos 37 degrees. 5 cos 37 degrees. Acceleration of this block A in this direction is A sine 37 degrees. Right? So A then turns out to be cos 37 degrees, by the way, is 4 by 5, and sine 37 degrees is 3 by 5. So A then turns out to be 20 by 3 meters per second square. by 3 meters per second square. So option A. Option A. Problem numbers 6 to 9 are related to this situation. 6 to 9. There is this L-shaped structure. There is a thread. There is a block B of mass M. Connected to the wall and the ceiling as shown with these two threads, AB and BC. AB is horizontal, whereas BC makes an angle alpha with the vertical. Now we want to be able to answer the question. Now, in this state, we want to be able to find the tension in the two threads, right? Look at the free body diagram of B. There is tension T1 like this, there is tension T2 like this, and there is weight mg like this. Yes or no? Right? So there is T2 like this, there is T1 like this, and T2 makes an angle alpha with the vertical, right? This angle is alpha, and then there is mg downwards like this, right? Now for equilibrium, horizontal and vertical forces must add up to 0, right? So very clearly, vertical forces, T2 cos alpha must take care of the weight, right? T2 cos alpha, whereas T2 sin alpha, this is T2, T2 sin alpha must take care of T1. Yes or no? Right? So T2 is mg by cos alpha, T2 is mg by cos alpha from this equation into sin alpha is T1. That gives me T1 equal to mg tan alpha. T1 is mg tan alpha. Plugging T1 equal to mg tan alpha, I get T2 equal to mg sec alpha, isn't it? Plug in T1 equal to mg tan alpha, sin alpha will get cancelled. T2 would be mg sec alpha. Yes or no? In this state, these are the tensions in the two strings connected to the mass M, producing equilibrium in the mass, right? Now, can I wipe this off, right? I expected all of you to get this right. Now what is done is, the string AB is snapped. This string, this is AB, and the string AB is snapped. Given that the string AB is snapped, what is the tension in the string? BC. What is the tension in the string? BC. That is what we want to find, right? BC is T, tension in the string BC is T, this is mg downwards. See, the differences, you know, this string, before AB was snapped, had tension T2, right? But after AB is snapped, it is impulsive and its tension suddenly changes to T. Right after AB snap, the tension in the string abruptly changes to T. However, if this was a spring, then after AB is snapped, its tension will not change. Abruptly, it would have maintained status. It would have maintained a tension T2. That's the difference between a spring and a string. If this was a spring, then even after AB snapped, right after AB snapped, its tension will be maintained T2 for a while. But since this is a string, it will not maintain tension T2. Its tension would abruptly change to T. Why? Because spring is a impulsive element. String is an impulsive element, whereas spring is non-impulsive, right? Now, what is it that we need to obtain here? We need to compute the tension in the string BC right after the string AB is snapped, right? See, let me examine what's going to happen to B right after this. Do you realize B would move in a circle of radius BC centered at C? Yes or no? Because this length will remain fixed. The trajectory of B would be a circle whose center is C and whose radius is BC? That would be the trajectory, yes or no? And at this instant, the velocity of B is 0? Yes or no? Now, think of it. mg could have been resolved. This is alpha, mg cos alpha, and mg sin alpha. Right? mg cos alpha and mg sin alpha. That's how you could resolve mg. What's the net force in this direction, along the radial direction, directed towards the center? T minus mg cos alpha? Yes or no? That's a net force directed towards the center in the radial direction. And this must provide the necessary centripetal force. Centripetal force is m into v squared divided by r. R is BC. But v is 0 in this case. V is 0 in this case at this juncture. It will build velocity in a while, but at this instant, v is 0. Yes or no? This leads us to believe that T is mg cos alpha. So see, the tension in BC has abruptly changed. It's an impulsive element. If this was a spring, it wouldn't have abruptly changed. See, the trajectory of B is going to be a circular trajectory. This is C, which is a fixed point. This is B. B will move in a circle. B will move in a circle, right? Of radius R. R is BC. mg is like this. mg resolved as mg cos alpha along the radial direction and mg sin alpha in the tangential direction. This is mg sin alpha. This is mg cos alpha. The free body diagram of B is T acting like this in the radial direction, mg cos alpha in the radial direction, and this is the tangential direction. mg sin alpha will cause B to develop velocity in the tangential direction, whereas T minus mg cos alpha would be instrumental in providing the required centripetal force, right? Right? If it has to move in a circle, it would have a centripetal force requirement, but at this juncture, the velocity of B is 0, right? So at this juncture, what is its centripetal force requirement? 0. mv squared by r. If v is 0, then centripetal force is 0, no? Right? That means T minus mg cos alpha at this juncture is 0. T therefore becomes mg cos alpha. Yes or no? Why? I don't understand how that happens. I don't understand how that will happen. How can the string be stretched? Damn thing, it's an inextensible string. The string is inextensible, dude. Who will stretch it? You will snap it in the process of attempting to stretch it. Right? Right. So option B, mg cos alpha, right? Now, so far so good, right? Huh? Let me read it, yaar. I have not read it. Let me read it. Huh? Yes, yes, please, please. Now, if the string BC is snapped, what is the tension in AB? BC snapped. Right? This is snapped. This is AB. Now what would happen to the mass M? It will move in a circle centered at A and radius AB. Right? That would be the trajectory of B. That would be the trajectory of B. Now at this juncture, what's the velocity of B? 0. T, if at all, it would have provided it the required centripetal force. But velocity is 0. T is 0. mg anyways, being perpendicular to AB, has no component in this direction. So the only force in the radial direction is T, which ought to have been 0 in absence of velocity. Yes or no? So tension in AB becomes 0. See again, AB is impulsive, right? So after BC is snapped, its tension suddenly changes from T1 to 0. That's it. Those are the things that you should take cognizance of. Got me? Right? It wouldn't have happened if it was a spring. Can I wipe this off? Okay, so now what they say is this whole unit is placed in an automobile. Thing is placed in an automobile. And I want to give this automobile an acceleration A such that this is mg. Even after I snap the string AB, even after I want to give this carriage an acceleration A, such that even after I snap the string AB, it maintains an angle alpha with the vertical. This is what I want. All right. So I want to be able to find the value of A. Now, look at the free body diagram of B. There is mg downwards, right? And let's say now the tension in the string becomes T3. Tension in the string BC becomes T3. T3. This angle is alpha, right? Now under the influence of these forces, if B has to remain in this position, that means with respect to the carriage it should have no acceleration. If B has to remain in this state, then it should bear the same acceleration as that of the carriage. There would be no relative motion between B and the carriage. That means now the net effect of all these forces is that B, because of these forces, should bear the same acceleration A as that of the carriage, so that B stays in this position. Yes or no? That's the whole requirement, right? Which means now, in the vertical direction, net of all forces must be 0. B must have a horizontal acceleration A synonymous with that of the carriage. Right? No? T3 sine alpha must give this mass an acceleration A to the right, ma. Whereas T3 cos alpha should prevent vertical acceleration. That means T3 cos alpha must take care of the weight, so that there is no acceleration in the vertical direction. M only has an horizontal acceleration, same as that of the carriage. And then dividing this by this, you get A is g tan alpha. So the acceleration that the carriage must have should be g tan alpha, so that the string maintains a disposition of this kind. Yes, Ayush? So g tan alpha, A must be g tan alpha to the right. A must be g tan alpha to the right. With respect to the carriage, isn't it? Why, yaar? If it is in the left direction, then it will tilt leftwards, yaar. No, that's not what you want. You want it to stay in this position. This was the original position of BC. You want it to stay in this position. No, it should move. It can stay in this position if it has no relative motion with respect to the carriage. Only then it can move in this position. And the only way it can have no relative motion with respect to the carriage is if A is G tan alpha. Sort it out. All right. You know what is happening at your end, Ayush? I'll tell you why you are getting muddled. You are mixing cause and effect. You know, you are looking at A as a cause. And you are superimposing A's. And you know, that's why you are getting muddled. Please get sorted in your heads. Cause are the forces. Effects are the accelerations. What you are trying to do is, you know, it must have an acceleration A, as if acceleration is a force. You know, that is where, you know, you are getting very complicated in your head. Don't do that. Look at the causes. Look at these. Forces are the causes. And what these causes must do to the mass m is that it must give the mass m the same acceleration as that of the carriage. In order that there is no relative motion between B and the carriage. Only then it can maintain this position. Right? All right. So enough of what you have seen about the impulsive nature of the string, right? This passage gives you good idea of the fact that the strings can act abruptly, right? Now we have a string as well as a spring. So these are two blocks, A and B. Masses 2m and m respectively, connected by a massless inextensible string. This is a string. The whole system is suspended by an ideal spring, massless light spring, as shown in the figure. The magnitudes of accelerations of A and B immediately after the string is cut. So I'm going to snap the string between A and B. And subsequently, I want to find out what the acceleration of small m and 2m would be. Now, if I snap this string, obviously B will fall freely under gravity. It's going to be G. Tension in the string will abruptly become shunya. Yes or no? It's going to become 0. So M moves down with an acceleration G. Okay. Now let me look at this state. Let me look at this state of the spring. See, if I have to look at the free body diagram of A and B along with this string, then the force in the string is internal. Mother Earth exerts 3 mg downwards. Originally when it was in equilibrium, 3 mg downwards, and the spring therefore must exert 3 mg upwards so that A and B are in equilibrium. That means the spring force was originally 3 mg. The spring force was originally 3 mg. Yes or no? Right? Okay. Good. Now, I snap this. What would happen to the spring force right after snapping the string? It will remain 3 mg. Very good. It will remain 3 mg. Now, if you look at the free body diagram of A, that is 2m. There is 2 mg downwards. Mother Earth, it has got detached from the string, right? And the spring force right after snapping the string will not change. It will maintain status. It's going to be 3 mg upwards right after snap. Over a period of time it will change, but right after snapping the string, it's not going to change. Yes or no? That means on this mass 2m, what is the net force upwards? 3 mg minus 2 mg. mg upwards is the net force divided by the mass 2m. Divided by its mass 2m, that's going to be acceleration equal to g by 2 upwards. Acceleration g by 2 upwards. Yes or no? That means right after I snap the string, this will fall freely with g. This will have an upward acceleration of g by 2. Clear? has about one fixed pulley, spring passing over this pulley, connected to a mass M, and another mass M, spring of force constant K, and this is a string, whereas this is a spring, right? Now the blocks are at rest initially. String is burnt at this point, so that means this is burnt at this point. We want to find the acceleration of the upper block right after burning the string, right? We want to find the acceleration of this block. Okay. So originally in this state, right, very good. If I look at the free body diagrams of these two masses, M and M, Mother Earth does like a 2 mg to these two masses, and there is a spring force upwards. Originally in equilibrium, spring force Fs is 2 mg, right? Right? Now after I snap this string, what happens to the spring force? 2 mg, right? So look at the upper mass M, 2 mg. String has got detached, but there is mg still down there. The net force is mg upwards divided by mass M will cause this mass M to have an acceleration g upwards. What? What is part of? This is one spring. This is one full spring. I mean, it becomes very cumbersome to draw these gola all the way, right? So just draw it in a small portion, and so whatever is connected to it is spring only. All right? All right. Huh? Yeah, can there be a problem in which the data could be insufficient? That's what you're saying. Yes. For example, now I say, Ayush, on the road, find his acceleration. Data insufficient, yaar. Shivang could be giving you 5 kicks on your ass. I would have to have knowledge of that. For example, if he is doing that, right? The force that he applies on your posterior. Huh? I have never witnessed this. What law is that? Acceleration equal and opposite is a law unknown to me. Sorry, yaar. Sorry. Which planet did you emerge from? Acceleration equal and opposite is a completely unknown law to me. God, you're giving me butterflies in my tummy, yaar. For example, it would be like ball falling down with an acceleration g because of gravity, and Mother Earth moving up with g if accelerations were equal and opposite. Imagine, yaar, how funny, all of a sudden Mother Earth moving up with g. God. Boy, oh boy. And by the way, sine 37 henceforth, you should remember 3 by 5, cos 37, 4 by 5. These are almost like standard values. You must remember these. Now, number 12, there are two situations. There are these two identical springs of force constant K each, 37 degrees. 37 degrees. And there is a block of mass 2 kgs right here. And an equilibrium. The whole unit is an equilibrium. That's one. The second one is the same thing. Instead of these springs, you have strings. 2 kg block. Okay. Now, equilibrium initially, and in this case, this spring is snapped. In this case, this string is snapped. In this case, this spring is snapped. In this case, this string is snapped. Once we do that, we want to be able to find the magnitude of the acceleration of the mass here and the acceleration of the mass there. Right? That's what we want to be able to find. Clear? Now, in this case, the spring force, suppose, was Fs. These are identical, and spring force will always act along the spring. Right? And on this mass m, it will act like this. On this mass, it will act like this, Fs, initially. Right? Very clearly, you know, with the horizontal, it makes an angle 37 degrees. That means vertical component of these forces are Fs, 2Fs, sine 37 degrees. Are the vertical component of these two forces Fs sine 37 degrees, Fs sine 37 degrees. And they must take care of the weight, 20 newtons. 20 newtons. Right? This gives me Fs equal to 10 divided by sine 37 degrees means 3 by 5, which is 50 by 3 newtons initially. Right? Okay. Now, why I needed this initial state for the spring is that even after I snap this spring, this spring force right after that will still be Fs only, which would be 50 by 3 newtons. Yes or no? So, that helps. Now, if I look at the free body of this mass, after I snap this, it will lose equilibrium, right? Forces acting on this mass then would be like 20 newtons downwards, Mother Earth, right? And Fs like this, which is 50 by 3, right? Yes or no? This angle is 37 degrees. Right? Right? This Fs could be resolved as 50 by 3 cos 37 degrees. Right? 50 by 3 cos 37 degrees, which is 40 by 3 newtons horizontal. Right? 50 by 3 cos 4 and 50 by 3 sine 37 degrees, which is 10 newtons upwards, right? So, the net force on this mass is going to be 10 newtons downwards, 20 minus 10, and 40 by 3 newtons like this. This would be the resultant force. And the resultant acceleration would be along this. So what's the resultant force? Root 100, right? 10 square plus 1600 by 9. That's a net force along this direction, right? Root 100 plus 60. So 900, 2500. So 50 by 3 meters per second, newtons, sorry. 50 by 3 newtons is the net force. Divided by the mass, 2. That means 25 by 3 meters per second squared is the acceleration of this. This is the net force, 50 by 3. Divided by the mass, 2. That will give me 25 by 3. So acceleration of this first mass is going to be 25 by 3 meters per second squared, isn't it? This is the net force divided by the mass m. Clear? We're taken care of on this front. Now let's look at this. It will not help knowing the tension in the string initially. Why? Because after I snap the string, then that's going to be history anyways. Right? That's not important. Isn't it? You know what I'm saying? So after I snapped, it helped knowing the initial state of the spring, because initial and after are the same. But in this case, it doesn't help knowing. So why do an unnecessary computation of tension in the string initially? Because it's not going to remain the same after I snap this. Right? Now, the tension right after I snap this becomes T. There is 20 newtons like this. Gravity. Now tell me, what would be the motion of this particle, P? This is Q. What would be the nature of motion of this particle, P? Circular with center at Q and radius PQ. Right. This would execute circular motion with center at Q and radius PQ. But its velocity initially is 0. Right? What I do is I resolve this 20 Newton into, this is 37 degrees, into a component perpendicular to the radius and component along the radius. Yes or no? So this is 20 cos 37 degrees along the radius, perpendicular to the radius. That is the tangential direction. Right? 20 into 4 by 5, which is 16 Newton. Right? And in this direction, what would be the net force? 20 sine 37 degrees. So 20 into 3 by 5, which is 12 newtons. Now, can you tell me what T should be? 12. Because T minus 12 must be mv squared by r, v is 0. So T anyways is 12 newtons. But I don't need that. All that is important, realize, that means net force in this direction is 0. That means the only force that exists is in the tangential direction perpendicular to the radius, which is 16 newtons, causing an acceleration in this direction to be 8 meters per second squared, 16 by 2. Right? That means A2, the acceleration of this is going to be 8 meters per second squared. All that I need to find is A1 by A2 is what I am seeking to find. Ratio of the accelerations. Do you all understand this? Huh? Huh? Theta is 90 degrees. Two perpendicular directions, so this, right? So far so good, right? Not a problem. Shall we proceed? See, these are simple problems, but they will communicate all the elements that you require towards solving involved problems. Right? These are the ideas that you should be very sure of. So we have a system of two pulleys, a fixed pulley, this end fixed, This is a movable pulley. This entire thing is a spring, you know. Don't think that only this is a spring and the rest is a string. Right? This entire thing is a spring. All right. And there is a mass m here. Mass m here. And the whole unit is in equilibrium. The whole unit is in equilibrium. All right. Now, in the process, you know, this spring must have got elongated by an amount x. If it gets elongated by an amount x, the spring force would have become kx in this equilibrium position. Say x1, right? It would have got in this equilibrium position, the spring would have got elongated by an amount x, causing the spring force to be kx like this. If I look at the free body diagram of the pulley plus mass, right? This pulley plus mass, it's going to be kx like this, and it's going to be kx like this, kx1, say x1. x1 is the elongation in the spring initially to produce equilibrium. So, and then there is mg downwards. What does that mean? What does that mean for equilibrium? 2kx1 must be equal to mg. Such must be the initial elongation x1 prevalent in the spring, right? 2kx1 must be equal to mg. Right? That total elongation in the spring. Convoluted, but over and above its natural length, it had an elongation x1 in order that the adequate spring force could be produced to balance the weight. 2kx1 must take care of the weight. Right? Now, next what is done is, you know, this movable pulley is moved down further by an amount x. Is moved down further by an amount x. Clear? Now if it is moved further down by an amount x, see, the spring was originally going this way. This was the state. Now, this part would have to, this portion to the left of the pulley would have to get elongated by an amount x. This portion to the right of the pulley must also get elongated by an additional amount x. That means now the spring in the new state, this is the new state, would have got elongated by an additional amount 2x. By amount 2x, isn't it? In the entire length, there is an x additional elongation x here, and there is an additional elongation x here. That means total elongation increases by 2x. That means now in the new state, the spring force in this new state, the total elongation is k into 2x plus x1. x1 was the original elongation. When I bring it to the state, additional elongation of 2x, so 2x plus x1, and k into 2x plus x1. That's the force owing to the spring. Then there is gravity downwards, right? Yes or no? The net force upwards minus mg, right? Net force would be this minus mg. That means 2k into 2x plus x1 minus mg is the net upward force. Is the net upward force acting on the mass? Right? Is the net force acting on the system? Mass plus the small pulley. Mass is light anyways. The pulley is light anyways. But 2k x1 will take care of the weight. 2 is equal to mg. That means the net force is 4kx is the net upward force, because 2kx1 is equal to mg. Right? So 4kx, right? And 4kx divided by the mass m will be the acceleration of the mass. So 4kx is the net upward force on this unit, and the total mass of this unit is m. So this would be the acceleration upwards of the mass m. After I, from the equilibrium position, pull the pulley down by an additional amount x, it will have an acceleration 4kx by m upwards. Because over and above the equilibrium forces, there would be additional forces because of additional elongation in the spring. There would be additional forces that would crop up in the spring, creating an unbalanced situation and a state of acceleration on the mass m. Right? So now there is a spring balance here. Two pulleys, fixed pulleys. A 20 kg block here and a 20 kg block here, right? A spring balance here and a 20 kg block here. That's situation B. And in situation C, spring balance, unequal masses, (20 kg and 10 kg), 20 kg and 10 kg. Okay. Now, in each of these cases, we want to find the reading of the spring balance. Hey, a spring balance is essentially a spring. What it reads is the force in the spring. What it reads is the force in the spring is what it reads, right? Now in this case, see, all of this is one single spring, all right? If you look at the free body diagram of this, what is this? 20 G downwards, and there is force T upwards. In this case, you know, there would be no acceleration. Identical masses, there would be no acceleration. So T must be equal to 20 G. And in this entire unit, therefore, the tension is 20 G. So the force in the spring is 20 G. The reading of the spring balance is going to be 20 G. Yes or no? In this case. Ball. Ki bolchish? It is the force in the spring. Don't add Mother Earth's forces unnecessarily without rationale. It's the force in this that will be the force in the spring. So the acceleration of this is 0. So the force in the spring must balance this weight. The force in this spring must balance the weight. T is the force everywhere. Oh, what? That is... Oof. So what? So they are acting on different bodies. Look at the free body diagram of this. I mean, force acting there is 4 newtons, 4 acting on this is 6 newtons. So what do you do to that? Does it mean force act? So what? But the tension is the same everywhere. It's not that, you know, the tension will get added. Did we see in a situation like this, look at this normal pulley. You know, you guys will also have to do some work at home. Look at this pulley, ordinary pulley, fixed pulley, all right? This is the tension T here, this is the tension T here. Does it mean the tension in the string is 2T? Booty. Does it mean the tension in the string is 2T? Then keep adding tension. This is a baap re baap. Same, obviously the same, yaar. Just because, you know, I've drawn this calibrator here doesn't mean, you know, there is something complicated. It's just one spring, one unit. This is... ki bolchish. Do you add the tensions here? 2T? What is the tension here? Huh? T. Why did you not add? Mago. Okay. So this part is clear. Can I move to this if you allow? Huh? All right. In this case, what does this T do? This 20G? This T also balances 20 G. That means the tension here is 20 G. Tension everywhere will be 20 G. So what would be the reading of the spring balance? 20 G. Okay. Right? Now in this case, the two masses will not be in equilibrium. They are unequal. So there is going to be an acceleration. There is going to be an acceleration, yes or no? And did I tell you one way to compute the acceleration of this is like, as if imagine this 20 G to be like this, something connecting this, 10 G to be like this, right? When I open it up, 20 G and 10 G, and the total acceleration then is going to be 10 G, 20 minus 10, 10 G divided by the total mass, 30. Yes or no? That will be the acceleration, which makes it G by 3 is the acceleration, yes or no? 20 G minus 10 G divided by 30. So G by 3 is the acceleration. Now, let's say the tension in this is T. This is 20 G. And under the influence of T and 20 G, it has an acceleration G by 3 downwards. So that gives me 20 G minus T is 20 G by 3, mass into acceleration. 20 G minus T is 20 into G by 3. T then turns out to be 40 G by 3. That's the tension in this string, and that would also be the reading of the spring balance.